Hello everyone, this is a presentation for our project conducted at the 7th Spectroscopy Winter School. Our research titled Application of chitosan, graphene oxide, titanium dioxide as gas sensor. Our team members are Khaled, Mohammed, Amgad, and Mahmoud with Dr. Medat and Dr. Hanan as supervisors. Our objective is to design a gas sensor starting with choosing the right materials, conduct modeling, and do a density function theory, DFT, to calculate the electronic properties and the reactivity for sensing applications. Then, after preparation and characterization for the material's composite, sensing experiment for the studied gases will be conducted. The subject for the school was about the use of biomaterials in various applications, so chitosan, a biodegradable, cheap, and easy to produce, doubled by its high surface area, it was chosen as our BAS polymer. Graphene oxide was used to enhance chitosan duo to its high electrical conductivity, large surface area, thermal stability, and mechanical strength, as well as the presence of functional groups which can act as active sites and helps in both sensitivity and selectivity. Titanium dioxide, a low-cost semiconductor which will help in electrical conductivity. It's chemically stable and have a reactive surface, allows for gas adsorption. These are the proposed modeled structures, where A is chitosan consist of 3 units. B is graphene oxide. C represent chitosan interacting weakly with graphene oxide, making a composite. And D is chitosan graphene oxide with titanium dioxide interacting weakly with the carboxyl group of graphene oxide via titanium atom. The studied models were conducted to DFT calculations using Gaussian 9. B3 LYP functional and LANL2DZ basis set were used based on its good combination of accuracy and computational cost. Geometry optimization as well as key physical parameters was calculated, including total dipole moment, HOMO-LUMO energy gap, global reactivity descriptors, molecular electrostatic potential, and density of states. The first table displays the total dipole moment and energy gap for the studied structure. A lower energy gap and high total dipole moment indicate reactivity and the ability for a molecule to interact with its surrounding. The energy gap of chitosan was 6.9 electron volt. After the composite formation with graphene oxide, we noticed the reduction in energy gap and decreased further after the addition of titanium dioxide. Total dipole moment significantly increased at from 5.8 to 14.4 dBi. The second table is the global reactivity descriptors, ionization potential, electron affinity, chemical potential, absolute hardness, absolute softness, and electrophilicity index. The chitosan graphene oxide, titanium dioxide show higher electron affinity, more chemical reactivity, higher softness, lower hardness, and high electrophilicity index. All means high reactivity and easily polarized, facilitating charge transfer. Molecular electrostatic potential can show the active sites and the overall charge distribution for a molecule. Molecular electrostatic potential contours for the optimized structures shows red colors around the oxygen atoms, where red means negative potential. Here is the density of states for the structures. The chitosan graphene oxide titanium dioxide shows more states in the unoccupied orbitals and smaller band gap than the constituent alone. The calculated HOMO-LUMO orbitals for the structures are presented here. The calculation of HOMO and LUMO gives information on the transfer of charge within the molecule HOMO-LUMO, shifted to the GO molecule. When titanium dioxide molecule is added to the chitosan graphene structure, charge transfer interactions appear stronger in the TiO2 system, with localization of LUMO on the titanium dioxide and HOMO on the graphene oxide. The chitosan graphene oxide titanium dioxide composite is to be interacted with gas molecules and its electronic properties to be investigated to access sensing mechanism and its sensitivity and selectivity. The proposed gases are humidity, carbon dioxide, and methane. The composite was proposed to interact physically with the gas molecules for reusability as gas sensor. This is the first interaction with the H2O molecule. The total dipole moment and energy gap changed upon interaction, signifying successful sensing. The molecular electrostatic potential contours indicates the composite is still reactive for further interaction. The total dipole moment and energy gap for the chitosan graphene oxide titanium dioxide with the 3 gases. The results show that the interaction with the carbon dioxide is favorable with lower energy gap and highest total dipole moment. The projected density of states and MESB for the composite interacting with the gas are presented here. The carbon dioxide shows more modulation in the density of states. Adsorption energy were calculated. Results showed significant selectivity for CO2 adsorption, where adsorption energy have a value of -0.104, indicating a spontaneous interaction. Quantum theory of atoms and molecule analysis was conducted to investigate the stability of the structures and the nature of the bonds formed with the gas molecules. The structures showed stability in the formation of hydrogen bonds, and the proposed and preferred weak interaction with the gas molecules was verified by the values of electron density and its Laplacian. The preparation of the chitosan graphene oxide titanium dioxide composite was prepared with different concentration using casting method as illustrated in the scheme. Here is some photos of the preparation process. To dissolve the graphene oxide, the samples were to go under sonication for homogeneous solution. Fourier transform infrared (FTR) spectroscopy was utilized to identify functional groups and characteristic peaks. Band assignments are recorded in the table. The chitosan graphene oxide titanium dioxide composite demonstrates significant potential for gas sensing applications due to its tailored physical and electronic properties. The combination of chitosan, graphene oxide, and titanium dioxide creates a synergistic effect, resulting in improved conductivity, increased surface area, and modulated electronic band structures, all crucial for effective gas molecule adsorption. Notably, the composite material exhibits a distinct selectivity towards carbon dioxide, likely attributed to a combination of factors, including specific interactions between CO2 molecules and the surface functional groups of GO. Future work includes experimental validation, further characterization, and sensing experiment is yet to come. Special thanks to Dr. Medad Ibrahim and Science Cafe team, and to the 7th Spectroscopy Winter School for this opportunity. Thank you for your listening.